Hey everybody, how's it going? This will be homework help video for 2.2. There's a couple topics that I didn't cover in detail in the videos for this section in this homework, and these are important topics, and I think really the best way to learn about especially 9.7 and 9.8 is just through examples, so I might as well help you out by showing you examples from your homework. First off, though, I'm going to do one from 9.5. The new thing in this section is that we're dealing with proportions rather than means, and a couple of special things happen with proportions. So I wanted to make sure that you were aware of those in advance. So let's take a look at this question. It says, according to a research center, 21% of all merchandise sold in a particular country gets returned. A department store in a certain city sampled 80 items sold in January and found that 28 of the items were returned. And then it's asking us point estimate of the proportion. That's just P bar. And that's just how many were returned out of the sample of items, 80. So 28 divided by 80 is going to be 0.35. Construct a 95% confidence interval for the proportion of returns of the store in the given city. So we need a margin of error to do a confidence interval. I'm going to use the built-in formula in Excel for that. We're going to do confidence.norm. We're doing norm and not t because we're doing a proportion problem, and we pretty much always use z in a proportion problem. There's weird cases where you don't, but I don't think you ever confront those in this class. Alpha, if we're doing a 95% confidence interval, then alpha is 5%, the area on the outside. The standard deviation in this case is the square root of 0.35 times 1 minus 0.35. Notice that's the standard deviation. It's not the standard error. Excel will calculate the standard error in the background for us when it takes account of the sample size, which is the last thing it asks for, which is 80. So let's double check it. Confidence, that gives me a margin of error. Norm, because it's a proportion problem. 0.05, 5% is the area in the tails outside of the 95%. The standard deviation of a proportion is the square root of the proportion times 1 minus the proportion. So that's the standard deviation. And then 80 is the sample size. So that looks good. Then I'm going to do my confidence bounds. So CIL for the lower bound and CIU for the upper. Lower is my point estimate minus my margin of error. Upper is my point estimate plus my margin of error. So that looks like 0.2455, 0.2455, and 0.4545, 0.4545. Now C, is the proportion of returns at the store in the given city significantly different from the returns for the country as a whole? Provide statistical support for your answer. One thing I want to show you now is that 21%, that's our null mean, that's going to be down here, these 0.21, that is not inside the 95% confidence interval. So that actually already provides some statistical evidence that this 35% is in fact statistically different from this 21%. So I just wanted to point that out, that there is a strong connection between confidence intervals and hypothesis testing. They're not like totally different things. Because we're going to find, I'll tell you just the secret's out, we're going to find that it's statistically significantly different. One really big clue that we're going to find that is that 21% is not in between 24.5% and 45.5%. So I just wanted to point that out real quick. We have a key phrase right here, different from, so that's a two-tailed test, right? There's literally only one option for a two-tailed test here. It's right there. because that's the equals and not equals. Another say of not equals, way to say not equals would be to say different from. And remember, the alternative hypothesis follows the research question. So different from, different from. That's the mathematical symbol for different from. Find the value of the test statistic. So let's go back over to our calculator. We have P0. That's going to be the null proportion. That's 0.21. We need that, right, for the test statistic. We're also going to need a standard error for the test statistic. This is where things get a little bit weird with proportions, and you have to be careful. Remember that we used 0.35 to calculate our standard deviation when we did the confidence interval, because that was our point estimate. But in a hypothesis test, we basically assume that the null hypothesis is true and then ask, what's the probability of getting this p bar if the truth is this? Well, if we're assuming that, then we should really use that for our calculation of the standard error, right? So that's a mistake that students often get into. Which proportion should I use for the standard error? If you're doing a hypothesis test, you use the null proportion right here. So the standard error is going to be equals square root 0.21 times 1 minus 0.21 parentheses divided by 80. Notice up here when I was doing the standard deviation, I didn't divide by 80. I just told Excel in the formula that it was 80. This is what it did for us in the background. Like Excel knows the formula for the standard error, and it also knows what it needs. That's why we fed that formula the sample size. So there's our standard error, and now we're ready to make a z, or a test statistic. It's a z in this case because it's a proportion problem. That will equal p bar minus p naught divided by the standard error, 3.07. Looks pretty good. Find the p-value. So now we're also adding to this evidence, right? So now this says that 0.35 lands more than 3 standard errors away from 0.21. More than 3 z statistics away from 0.21. And you hopefully now are starting to see that that's quite a few standard errors. Like thinking about confidence intervals, we're always adding and subtracting about 2 standard errors, like your z statistic 1.96. The t statistics are usually a little bigger than that, about 2.1. So we're landing farther away from that, right? So now let's figure out the probabilities. We need the p-value. So we'll start by finding the probability of being greater than z, because we want that upper tail. So let's equal 1 minus. I'm doing a probability to the right. The formula norm.dist gives me the probability to the left, so that's why I have to do 1 minus to get the probability to the right. What number? This one. What's the mean of the standard normal distribution? What's the standard deviation of the standard normal distribution? Always true here. Now we're ready to calculate our p-value. I would stop there if I was doing a one-tailed test, right? But I'm not. I'm doing a two-tailed test, which means I have to multiply the one-tail p-value by 2. So that's going to be 0.0021. And that's a less than alpha, right? They told us alpha was something or the other. I think they told us it was 0.05 somewhere. Where did you tell us? Oh no, they told us it was 0.01, which is 1%, but this is still less than 1%. This is 0.2%. So our p-value is less than alpha. Another way that's the statistical jargon way of saying it. P-value is less than alpha, reject null hypothesis. The actual real world way to say it is the probability of observing a 35% item return rate, if the true rate is 21%, is less than 1%. The probability of observing a 35% item return rate, if the true item return rate is 21%, is only 0.2%, very low. So I say this evidence that I've gathered is inconsistent with this store having a return rate of 21%. So I will reject that idea. So let's look at this one. Reject the null. That looks good. There is insufficient evidence to conclude that the return rate for the store in a given city is different than. No, that's wrong. We do have sufficient evidence. So that part is right, but that is not an interpretation of rejecting the null. Here's our other option. Reject the null. There is sufficient evidence. So that right there is going to be our answer. Okay? So I just opened the solution. So A, 0.35, 0.35, that looks good. B, 0.2455, 0.4545. So that looks good. C, we did the p-value, there it is, 0.0021. Reject HO, there is sufficient evidence. So that's the one we picked too. Now note, because this is something that comes up on the exams, we are displaying rounded intermediate values for practical purposes. However, the calculations are made using the unrounded values. That's what we did over here. And that's what I expect from you on the test. I never rounded until I put the answer into the box, right? And even after that, when my new answer depended on old answers, I still never rounded. I only rounded at the point when I typed the number in the box. That's what you should do on the homework, and that is what you should do on the exams. So let me know if you have any questions about that. I also encourage you to just use Excel as a calculator like I've done in this problem. Your life will get easier in the long run if you start doing that, especially in this class. You're going to have to make the transition at some point for later in this semester. Now is a better time to do it. I promise your life will be easier if you start just practicing those things. At first, you might have to do it both ways, which is fine. But eventually, you'll get used to doing it Excel, and that's a valuable skill to have too. So this was HW 9.5, number 4. Now we're going to check out HW 9.7, number 1A. So let's open that up. So yeah, stay signed in. God. Let's see. Preview? No, we don't want this assignment anymore, dude. We want this assignment. Preview. Ooh. You may need to use the appropriate appendix table or technology to answer this question. No, you should never click on those, you guys. Consider the following hypothesis test. The null hypothesis is that the true average mean is greater than or equal to 10. The alternative is that the true average mean is less than 10. So we have a lower tailed test, a left tailed test. We're only looking for values below the null mean to see if we should reject or not reject. So the sample size is 130 and the population standard deviation is assumed known with sigma 5, alpha is 0.05. So I'm going to start writing this information down. What do we got? What do we got? We have a null mean, so I'm going to call that mu naught. This letter is said mu naught, mu naught. That's 10. That's always the number that appears on the right side of the hypothesis test. N looks like something we're going to need. 130. Alpha, or no, sigma, or I'll call it the population standard deviation, because that's what I've done in the past, and I think that's a good way. 5. Alpha, 0.05. Okay, so I'm just right now, all I'm doing is like writing down these numbers. Now, look at this. If the population mean is 9, so that means they're telling us true mu. They're telling us what it is. It's 9. So you wouldn't, like, the whole point of hypothesis testing is that we don't know what the true mu is, but you still might want to do problems like this in the real world. Imagine you work at a car manufacturer and the Transportation Safety Board does tests on airbags and says, okay, your airbag test needs to return an answer between above 9, right? Above 9. Well, what if you didn't really know? It's a sample. Like, the true average of any mechanical system probably varies a little bit, right? For environmental reasons, equipment differences, small differences like that. So you might want to design a hypothesis test in that situation to be like, I need to figure out what the probability of me being even able to find out that I'm violating this thing is. And that's what these problems are all about. Because we're going to figure out if the population mean is 9, what is the probability that the sample mean leads to the conclusion, do not reject HO? So let's think about what that question is really answering. If the truth is that the mean is 9, then the alternative hypothesis is true, right? We want this to be our answer at the end of the day, because the truth is consistent with the alternative hypothesis. However, we know that when we take a random sample, it's possible that we'll get 9.5 as X bar. And 9.5 might lead us to conclude, you know what, that's not far enough below 10 to reject the null hypothesis. We might get a big p-value, in other words. And then we'll say fail to reject. That would be the wrong conclusion, and that's called a type 1 error. Or sorry, that's called a type 2 error. A type 2 error occurs when the alternative hypothesis is true, but we fail to reject the null hypothesis. That's called a type 2 error. And we can actually figure out the probability of that occurring with these numbers. So let's go to the notes real quick. We have a situation in this problem like this. We have a null mean, mu, is greater than or equal to 10. And more generally, we have a situation where mu is greater than or equal to some null number. In this particular case, that number is 10. The alternative, of course, then, is that mu is less than that number. Now, in this problem, notice that if the population mean is 9, they're saying like, hey, this is true. They're telling us that in the problem. They're saying the alternative hypothesis is true. How are they saying that? They're telling us that the population mean is in fact less than 10. Okay? So we could draw out this situation. The unknown truth, so we're kind of like, we know it's 9, but when we're doing the hypothesis test, we don't. So we're kind of like pretending we don't know when we draw these. We have some unknown truth down here. The true mu. That's what our question is about, right? The true mu. So let's imagine a case where that truth is less than to the left of, right? If this is a number line, this mu is less than mu naught. So now this is consistent with this problem. Mu naught is 10, mu is 9. 9 is less than 10. So this is general. So this is a general case, but it's consistent with this problem. So the question is, what's the probability that I fail to reject mu naught, the null hypothesis? Well, now we have to kind of step back and think about how hypothesis testing works. So with a hypothesis test, I'm setting up my null distribution centered at the null mean right here. And then there's going to be some critical value over here, right? That if I land to the left of this in the green area, I'm going to reject the null hypothesis. And that's a good thing in this case because that's what I want to do. The truth is that the alternative is the alternative hypothesis. I want to reject the null. If I land with my X bar, my sample mean, to the left of the blue line, then I will reject the null hypothesis, which is what I want to do in this case. However, if I land to the right then I will fail to reject the null hypothesis. And that's a type 2 error. This problem is basically asking us to calculate the probability that is represented by the blue area, given that the truth is 9 and the null is 10. So this is kind of the problem setup. And so this blue line, I like to call that the critical mean. So we're going to have to calculate that. If we land to the right, we'll fail to reject, and we'll make a type 2 error. If we land to the left, we will reject, and that's good. That's what we want. The blue area is called the probability of a type 2 error. Another way of saying that is the probability of failing to reject a false null hypothesis. The green area is actually called the power of the test. We like the green area. The green area is if we land in there, we get the correct answer. If the blue area, we land in there, we get the wrong answer. Notice that the green area plus the blue area add to 1. In other words, the probability of a type 2 error plus the power of a test always add to 1. So let's bring this to the numbers now. So it's really important in these problems to conceptually think about what we're doing, often using diagrams. And I encourage you, I hope that you're drawing bell curves like this in the problems. We have to do this basically. I have to do this, even though I have a lot of experience, to wrap my head around how to do these problems. So let's go back to our information. So what are we going to need to calculate? Well, I want that blue area. So the first thing I'm going to do is calculate the critical mean. I need to figure out what number between 9 and 10 will lead me to reject the null if I land to the left of it. Okay? Well, notice that I know this little area right here, that rejection region, that's 5% in this problem. How do I know that? Because it's a one-tailed test, and alpha is 5%. So let's calculate the critical mean. And for that, by the way, I'm going to need my standard error. My standard error will be the population standard deviation divided by the square root of the sample size. Okay, that's my standard error. Now my critical mean is going to be the number, the x bar, such that I have 5% to the left from a distribution centered at 10, the null, with this standard error. So equals norm.dist, or actually norm.inverse, right? Because I know the probability to the left. The probability to the left that I need to find is that alpha, 5%. So that's 5%. Comma, the mean of the distribution I'm looking at right now, I'm looking at the black one to identify this little area right here. This triangle has 5% in it. Notice that I'm using the black distribution for that. What's the mean of that one? 10 in this problem, because that's my null distribution. So that's 10. The standard deviation is the standard error. Okay, so what this is going to give me, this critical mean, it's going to give me the number that has 5% to the left of it in a distribution, a normal distribution with 10 in the middle and with this standard error. And that makes sense. I told you guys the number would be between 9 and 10, right? Well, it has to be. Here's 9. Here's 10. Of course, wherever this line is, makes sense that that would have to be 10. Actually, maybe if it was really close, I think it always has to be between 9 and 10. But I can maybe imagine it being less than 9 if this distribution was really spread out. So that is the number. So let's just interpret it this real quick. The probability of landing to the left of 9.278684 in a distribution centered at 10 with this standard error is 5%, because that's how we figured out the number. We asked Excel to tell us the number from a distribution centered at 10 with this standard error that has 5% to its left. Why did I use norm, by the way? Because this problem told us the population standard deviation. Okay? So I've figured out the critical mean. Now I have to figure out the blue area. That's the answer to this question. Because if we land in the blue area, we will conclude do not reject HO. So we need to figure out the probability in the blue area. So that, notice, will be probability of being greater than critical mean. That's what we're figuring out. In this particular situation, we're finding the probability of being greater than the critical mean. So that's going to equal 1 minus, because I'm going to the right in the blue area, right? 1 minus norm dot dist, because now I'm calculating a probability. To the right of what number? The critical mean. Standard deviation is this number, because that's going to be the same. Notice that in this problem, the standard error is the same for both of these distributions. It's 5 divided by the square root of the sample size for both distributions. So that's the same standard error. But the mean, so now, oops, I put in the mean in this distribution. This is important. Sorry, I skipped the mean and jumped to the standard deviation. Which one of these distributions is our sample actually coming from? It's coming from the true distribution. So notice now I have to write 9 as my mean, because that is the actual place where my data is coming from. That's what the problem said. The true population mean is 9. They tell us right there. Now I'm ready to put in my standard error, standard deviation of the mean, and then true, of course. And so my probability of being greater than that critical mean in this problem is 0.262. So that's the area in the blue region. That blue region, again, is the probability of not rejecting this hypothesis. And now we've calculated. So let's a little review what we did. This is the null hypothesis, null mean. They told us all this. The sample size is 130. Population standard deviation, alpha, 5%. The true mean is 9. They told us that in the problem. Standard error is just the population standard deviation divided by the square root of the sample size. Now the critical mean, remember, I had to figure out what number breaks this into my accept null hypothesis region, reject null hypothesis region. We figured that number out using 10, the null mean, using alpha, how much area is to the left of this blue line, 5%, and the standard error, of course. And then once we had the critical mean, we could ask, okay, well, I'm pulling my data from this red distribution. What's the probability I land to the right of the critical mean? 1 minus norm dot dist. E9 is the critical mean. 9 is the true mean. Standard deviation, and of course, we always write true in these distribution formulas. So 0.2626. Okay. So let's take a look at some of our, so these are the explanations. Remember, their practical purposes, the rounding, because I can't put these huge numbers in here. SE, the standard error of X bar is 0.44, 0.44 if you rounded that. Now they're saying, here's this critical P, 9.28, 9.28 rounded. Notice this is the one centered at 10, because that was our null one. That's where we use that to generate the critical mean. Now, that's how they figured out the critical mean with some fancy formula, but luckily Excel does all that work for us. They jumped, by the way. They're doing extra work because Excel is awesome because it doesn't care which normal distribution you have. We did not have to convert this to a Z. You could, but you'd have to do a little bit of extra work, which is what they're doing right here for part A. That's why they're calculating this as Z. But Excel is awesome. You don't have to do that. Like you can tell Excel any mean and standard error, standard deviation, and it'll give you the probability. So we just jumped straight from our this distribution to the critical mean. We didn't do the intermediate step of finding the Z-score. And then we just calculated the probability of being to the right of that, which is 0.2626. And that's 0.2626 right here. Okay, so that's how we do those problems. Be sure to let me know if you have any questions about that. Those are complicated. Don't feel bad. You really have to stop and think about what's going on with this diagram. I strongly encourage you, like, don't just sit there and try to be like, type, new number. You have to sit and like think about what the meaning of this diagram is carefully and the context of this question too. And so make sure to reach out to me if that's confusing me. I'm happy to meet with you about that because that is probably conceptually one of the hardest things